So electron configurations. We've talked about quantum mechanics and the behavior of electrons. Well, if you had to sum up the behavior of electrons in one word, what would you call it? Well, weird. Strange, perplexing, incomprehensible, disturbing, yeah. Uncertain, yeah, uncertain, definitely. So, electrons in atoms exist within orbitals, right? The orbital is a region of probability of finding the electron. I think the best way to think about an orbital is that it is the standing wave of the orbital, of the electron. The electron is a wave and a particle, and we can think of it as forming a standing wave, and that standing wave is the orbital. So the orbitals have designations like 1s and 2p, etc. And when we list those together to describe which orbitals are occupied in a given atom, that's called an electron configuration. So here's the electron configuration for hydrogen, which is pretty simple because there's only one electron. So that one electron is in the lowest energy orbital, which would be the 1s, and then as a superscript here, we put the number of electrons in that orbital. So there's one electron in the 1s orbital. This is one of the few places where chemists do write the number 1. So Schrodinger's equation can be solved for hydrogen, and calculations show that that one electron is going to occupy the lowest energy orbital in the atom. Exact solutions aren't possible for multi-electron atoms because there's additional terms for the electron-electron interaction, but approximate solutions show those orbitals to be very much like hydrogen's orbitals. And so we're going to call that good enough. The additional concepts that affect multi-electron atoms are electron spin and the energy splitting of sublevels, and that really complicates things. So an orbital diagram is a more visual depiction of where the electrons are in an atom. And here we use boxes and arrows. So for hydrogen, we have a box representing the 1s orbital. So each box represents an orbital, and this half arrow represents an electron. So the half arrow pointing up suggests this is positive 1/2 for the ms number, or we could have it pointing down, and that would be negative 1/2. So the orbital diagram, I think, works really well with my idea of the hotel. So I see those squares as being a lot like a bed, right? So here's a bed shaped more like a king-size bed, more square. There's the pillows, just to help you have an idea of top and bottom. And so that electron there is sleeping right side up in the bed. I don't know what he's doing with his hands. If we look at helium, helium has a second electron. That electron is spin down in the same orbital. So I imagine that as the other electron is sleeping upside down in the bed. You know, maybe he'd move the pillow, but you know, whatever. Okay, so that's what I'm picturing when I see this. These are beds, and we're putting the electrons to bed. So in a group of hydrogen atoms, the electrons can be spin up or spin down. About half of them would be each. And we can't really identify, well, this one's plus 1/2, that one's minus 1/2, because we're not looking at individual hydrogen atoms anyway. We're looking at large numbers of hydrogen atoms together. So instead of worrying about where that first one is, we're just going to always assume the first one is spin up. The arrow points up. So we have some principles, and I guess they're mostly called principles here. I'm not going to quiz you on the names of these. But the Pauli exclusion principle says that no two electrons in an atom can have the same 4 quantum numbers. So if we have 2 electrons that are in the same orbital, they're going to have 3 identical quantum numbers. And we'll look at that on the next slide. So that means the 4th one must be different. And this means that we can only have 2 electrons in an orbital, and they have to have opposite spins. So, yeah, that's nice. Here, let's look at this one. So here we have helium. Here's helium's electron configuration. Helium has 2 electrons, and so they're going to both fit in that 1s orbital. The orbital diagram is going to look like this, where we have 1 electron spin up and 1 spin down. And here are the quantum numbers for those 2 electrons. Both of these electrons are in principal energy level 1. That's what this 1 means. They are both in an S sublevel. 0 is for S. So that's something that we need to review a little bit. So that's L. When L is 0, 1, 2, 3, we call that S, P, D, and F. So they both have the same value of L. M sub L tells which specific orbital are they in. Well, in the S subshell, there's only 1 orbital. In the S room in the hotel, there's only 1 bed. So they have to be in the same bed. So that number is 0. And then we come down to the 4th number, and this is where there has to be a difference. We can't have 2 students at Fresno City College with the same student ID numbers. That would cause problems, right? We can't have 2 people with the same social security number. That would cause problems. Everybody needs their own number. Every electron needs its own set of numbers. You could also think of this as like a telephone number, right? If 2 different people have the same telephone number, that's not going to work. Everybody needs their own telephone number. So they have 3 numbers the same, but the last one is different. Any questions?
That's always been 4. Will there ever be a case where there's 3?
All electrons have 4 quantum numbers. We don't always identify what the spin is, but it does have a spin. So the sublevels in each principal energy level of hydrogen all have the same energy. I don't know about you, but I find level, sublevel, orbital, those different terms get a bit confusing, right? And so that the hotel helps me. There's floors and rooms and beds. Somehow that's a lot easier to keep track of. So here, this is the rooms in each floor have the same energy, the same cost for hydrogen. How much you pay for that room, how much energy the orbital has, just depends on the principal quantum number. That's for hydrogen. When we have orbitals with the same energy, those are called degenerate. So different beds that you would sleep in the hotel that cost the same amount of money are degenerate. For multi-electron atoms, though, the energies of the sublevels get split. They're not degenerate. So what we find is that different rooms on the same floor are going to have different costs. And it's caused by charge interactions, by shielding, by penetration. So in general, the lower the value of L, within a principal level, the lower the energy of the orbital. So say we're on the 5th floor of the hotel. We're on principal level 5. And there's an S room, a P room, a D room, an F room, etc. Remember, S corresponds to L being equal to 0. And P is 1, D is 2, F is 3. There are sublevels after that. We don't see them on the periodic table, but they do exist. And those would just follow the alphabet. So the next one would be G, and H, etc. So on, say, the 5th floor, the S room is going to be cheaper than the P room. The P room is cheaper than the D room. The D room is cheaper than the F room. As you go away from the elevator, the rooms get more expensive. Maybe because they're quieter, I don't know. Any questions? So Coulombs Law. Coulombs Law describes the potential energy of two charged particles. How much they are attracted or how much they repel each other. And this depends on the magnitude of their charges and on the distance between them. And this is similar to interactions that we observe in regular life with magnets. Right? So if you put a magnet on the refrigerator and it sticks, that's great. And then you put like 10 pieces of paper between the magnet and the refrigerator, is it still going to stick? Probably not, because you've increased the distance between the metal surface and the magnet. So in this equation, R is the distance between the two things. The farther apart they are, the less attractive force there is. Q1 and Q2 are the magnitudes of the charges. So if you have a really, really strong magnet, it can hold up 10 pieces of paper. If you have a really weak magnet, it might not be able to hold up even 2 pieces of paper. So the potential energy of two charged particles depends on how big the charges are and how far apart they are. This part up here is a constant, and it's nice, but we don't need to actually use that. In fact, I had a dream about epsilon last night. I was wondering where that came from. Okay. What we can remember more easily is that the energy is proportional to Q1 times Q2 divided by R. And remembering that proportionality can help us reason out a lot of things when dealing with charged particles. So if Q1 and Q2 are both positive or they're both negative, then E is going to be positive. Positive energy means these are repelling each other. For opposite charges, E is negative. That means the charges are attracting each other. We don't need to get hung up on the positive, negative, but we can remember that opposite charges attract and like charges repel. The potential energy increases as the particles get closer together. So if they were attracting each other, the energy gets more negative, which is more stable. If they're repelling each other, the energy gets more positive, which is less stable. So you think about, lifting up a piano above the ground. The higher it goes, the less stable it is, right? That's high positive energy. We want low negative energy. And then the strength of the interaction increases as as the particles get closer together. The basic idea is there. So each electron in a multi-electron atom, which is everything but hydrogen, experiences attraction for the nucleus and repulsion from the other electrons, because electrons are negatively charged. The nucleus is positively charged. So the electron is attracted to the nucleus, but it's repelled by the other electrons. So those repulsions reduce the net attraction that any one electron has for the nucleus. We say it's shielded from the nucleus. So we can look at an effective nuclear charge, which takes into account that repulsion from the other electrons in contrast to the attraction, and gives us an overall net effective or net nuclear charge. And that's called Z. Z is the atomic number, which would be the number of protons. Penetration talks about the electron getting closer to the nucleus. If if the electron can penetrate through those other electrons that are repelling it, then it can get a better picture, a better view of the nucleus, and it's more attracted to it. It gets closer. R gets smaller. And so the outer electrons that are better at penetrating the electron clouds of the inner electrons have more attraction. The degree of penetration is related to the orbital's radial distribution function. Now, I expect that most of that was just like Charlie Brown's teacher, blah, 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 right? Hopefully it'll start to make sense when we look at some pictures. So here we have a diagram of lithium. We have 3 protons in the nucleus, and in the first energy level we have 2 electrons, and the third electron is in the next out level. So if we think about the Bohr model, which we know isn't true, but it's easier to visualize, this one is in a larger orbit, right? And these 2 electrons are between this electron and the nucleus. So this electron is repelled by these electrons while simultaneously being attracted by the nucleus. And so the easiest way to think about this is, well, we've got a +3 charge here, and we've got these 2 electrons here, 2 negative charges, +3 minus 2, we get an effective charge of about +1 for this electron. These electrons get in the way of the attraction that this electron has for the nucleus. Does that make some sense? That's shielding. Okay, another kind of odd analogy. So think about going to a stereotypical Southern California beach, right? And you got the bodybuilders and all the beautiful people out there. If we've actually been to the beach, we know that those people are in the minority, and most of the people look like we do, like just regular people. But there's some beautiful people on the beach, right? You can go to the beach, and the guys are wearing Speedos, and the girls are wearing string bikinis, and like you could just see almost everything, right? And so we could be very attracted to that. So that's what this electron on the inside is seeing. There's really nothing between it and the object of its desire. Here, this one is looking through something that's obscuring its vision. So maybe some clothing, right? So here there's 2 electrons buzzing around it here. So when this electron sees the nucleus, it's like it's looking at this person wearing street clothes. You know, button-up shirt and a pair of khaki pants. And, well, the person's still attractive, but they're not as attractive. Does that make sense? I know, weird, huh? Yeah, but the weirder it is, the more likely you are to remember it. So then you can imagine, you know, that one's in the second level, a larger atom where, you know, maybe we've got something up here in level 6. This is looking at somebody, and they're wearing a parka and a ski mask and big boots, and I mean, you really can't even see any of their skin. You can't even tell what shape or what sex they are, right? So then your attraction for that person is gone way down because you can't even see them. Does that make sense? So the closer these electrons get to the nucleus, the fewer things are between them, the more attracted they are. You okay with that? So here's the idea of penetration. If this electron that was out here in this second level is able to get in among these other ones, now it can see better. I'm thinking actually the example of a crowd might be better than clothing, right? So here's the guy on the outside, and here's the attractive person, and there's this crowd of people, you know, clustered around them, right? And so this person can't see very well through the people. But here, if he can squish his way, penetrate between the people and get closer so he can actually see them, then there's more attraction. I think that might be better than clothing. Just made that up right now.
So it should be a celebrity.
Yeah, it's a celebrity, yeah.
So when is that electron able to penetrate? Like, what's the difference between?
Excellent question. When is it able to penetrate? I'm glad you asked. Here's the slide. So I didn't pay her to ask that question, but thank you. I appreciate it. So we looked at these radial probability graphs earlier, and they're a little hard to visualize, but there's a reason that we actually looked at them. So for the 1s orbital, this is the distance from the nucleus, and this is the probability of finding the electron at that distance. So we see at the nucleus there's 0 probability of finding the electron, and as we move away, we immediately start to get more probability, and it gets to a maximum, and then it starts to fade down. So it's kind of like a donut with a very small hole in the middle, right? So most of it's donut, and then it fades off. And so the 2s orbital has a node in it, and so it's got this little blip, this little ring on the inside, and then most of it's out here. But some of this orbital is right in there with the 1s orbital. So the electron, remember, is as a wave everywhere in that orbital. As a particle, it can only be in one place. But when we're not looking at it, it's both at the same time, right? So an electron in this 2s orbital can be right in here, which is just as close as the 1s orbital. So it's penetrating through the crowd of people around the celebrity. We're fleshing this out as we go along here. Pushing in, we want to see Robert Downey Jr. and, getting close, ooh, ah, right? This person, the 2s person, can get in there. Here's the 2p orbital. Now, the 2p orbital does overlap here, but down here where we're really close, and the closer you are, the more attraction there is, the probability is much less. So the 2p orbital is not able to penetrate through the crowd as much. It can maybe get through, but there's still a layer of people between you and the celebrity, so you can't see as well. Does that make sense? So because the 2s and the 2p sublevels have different amounts of penetration, that causes their attraction to the nucleus to be different. It causes the energy of those sublevels to be different.
So could you say if you 2s is a smaller person trying to go way through, and 2p is like a big person that's trying to push their way in a sense?
Kind of. I think it might be more better, instead of saying a small person and a big person, a pushy person and a not so pushy person, like a more polite person. So the 2p sublevel is more polite, and it's like, well, I'm going to try to get in, but I'm not going to offend anybody. And that 2s person doesn't care, and you're just going to elbow and dig in there and get in through there. I think that might be more accurate. So the 2s orbital then is lower in energy than the 2p orbital. Because those electrons can get closer to the nucleus, they experience more electrostatic attraction for the nucleus. Any questions?
So does that mean that an electron in the 2s orbital that's the same distance that you would find in the 1s orbital, does that mean that it's in the 1s orbital?
Well, that's an excellent question. So if those orbitals are overlapping, does it mean that that 2s electron is in the 1s orbital? Yes and no.
So we're like, you can't, it can be in two places at once, and maybe in the node, may not be in the node, maybe.
Well, they're never in the node. The node is zero probability, so it can't be in the node. But it can be here or out here somewhere. Those are different distances. If it's a particle, we can't understand how that could be. How could the electron be out here and later it's in here without going through this point? Not possible. But it's a wave, and a wave can have a node in it, right? So I'm not sure why I didn't show the picture or the video of the string. So we can make a standing wave on a string. It's a little lopsided, bear with me. So if you took a still picture of it, you'd see at some point that the string is in one place. But when we watch a video of the string, we see it being all over the place, right? It blurs together and it looks like it's occupying the whole space. The wave is over here, the wave is over here, and yet it's not in the middle. Because in that middle point, that the string isn't moving at all. So the electron is like this. It can be on both sides of this node. For the 2p orbital, where there's one lobe on one side of the nucleus and another lobe on the other side, it looks a lot like this. So if this is the nucleus, and we have one lobe of the p orbital, and then we have another lobe over here, I think of the p orbital as a standing wave of the electron. Now, can the standing wave of the 2s, the 2p, and the 1s be in the same physical space? Yeah, they can. And we could have a lot of questions about that. I don't know the answers to those questions, and it's beyond the scope of the class. It's one of the nice things about teaching an intro class is we can say, well, that's too advanced. And I don't have to admit that I don't know how that works.
So the 2s orbital, because it has proximity to the nucleus, is able to get closer. And even though the 2p orbital has more, like, it uses more or has more energy because it goes out farther.
It's higher in energy because it's further away.
Right.
So it's not as stable
Okay.
as the 2s.
Okay.
And the 1s is more stable because
Right.
it's in there all the time.
Okay. So its proximity is not it's getting it closer to the nucleus.
Well, the energy is related to the proximity.
So it's like inverse.
Right. And that's where Coulombs Law comes in.
Is that with the switch, like, or will it always be that 2p has more energy than 2s?
2p will always be higher in energy than 2s due to the shape. Yeah. And we could look at a similar diagram for the d and the f orbitals, but we don't want to do that. We'll just be okay with, oh yeah, the f orbital penetrates less than the d, and the d penetrates less than the p, and so we'll just be good with that. Yeah. So this is the idea of shielding. If we say Q2 is the charge on the electron, Q1 would be the effective charge on the nucleus. Whether I can have full effect of this celebrity's awesomeness, or whether I'm looking through one layer of people or 5 layers of people, right? So that reduces the attraction, and then the distance also has an effect. So the farther away, the less attraction there is. Okay? And they kind of go together. So the sublevels of each principal level are not degenerate because of penetration. The rooms of each floor are not the same price. Are not the same price because of penetration. When we get up to the 4th and 5th principal levels, the effective penetration becomes so important that the 4s orbital is actually lower in energy than the 3d orbital, and then things get all wonky, right? And there's different ways for remembering what the order is. I'm not going to show you any of the trick ways. I'm going to show you that it's all on the periodic table. So as you go farther and farther out, higher energy levels, the difference in energy between those levels becomes smaller and smaller, and that's why they're easier to get mixed up. And then just to make things more interesting, the relative energy ordering can actually vary among elements. So we're going to totally ignore that. We're going to say, well, yeah, okay, that's true, but we're just going to look at things where they behave themselves. So this is the general energy ordering. So if we see energy going up, the 1s is the lowest in energy, and here we have the second level, the 2s and the 2p. The 2p is a little higher. These three orbitals in the 2p sublevel are the same energy. So this is the 2s room, there's one bed. This is the 2p room, there's three beds. And you can imagine, how can you charge a different amount for one bed in this room? Well, that bed is $5 more than this other bed. Who's going to monitor that, right? It's not going to work out. All the beds in that room cost the same, doesn't matter what bed you sleep in. Then there's 3S and 3P and 3D. If we just look at the third floor, S, P, D, energy's going up. And so if you think of this red arrow here as the elevator, as you're going away from the elevator, the price gets more. But we would expect that this first room on the fourth floor would cost more than the 3D room, but it doesn't. This one's cheaper. So as electrons are coming in here, so you can imagine maybe a tour bus of electrons, and they're all cheapskates. And they come in and, they're checking into the hotel, and they all want the cheapest room. So, I don't know. Let's do manganese. I did iron yesterday. So here comes manganese. Manganese is a tour bus with how many electrons? Mn? 25 electrons. So we're going to put these in the hotel rooms, in the beds. We'll put the electrons to bed. So the first one's going to take the cheapest room, sleeping right side up in the bed. The next one comes in and is going to sleep upside down because that's cheaper. And then they're going to go start filling up the 2S room. And then the fourth one goes in there. And now we have to pay more money and go into the 2P room. Now this next electron has a choice. Sleep with this person he's not familiar with in this bed, or take his own bed. What would you do? Take your own bed. Would you sleep right side up or upside down? Right side up. And then the next one going into that room is also going to choose its own bed, right? That makes sense. The next one coming in, all the beds are occupied. They're cheap. They're not willing to pay more money to go up to the next expensive room. So now they're going to sleep upside down with another electron. So I think we're up to 10 there. And so then we get over here, here. And then we get into the P's again. And again, they're going to take their own orbital before they pair up. Now the next one is not going to go finishing up this third floor. They're going to go over here because that one's cheaper. Not sure why in the hotel. Maybe, I don't know. It's closer to the elevator. I don't know. Too noisy. But it is. And then we go up here. And now we're at we're at 20 electrons, so we need 5 more. The next most expensive room is the 3D room. And so we've got 5 more electrons. We're going to go 1, 2, 3, 4, 5. And so can you imagine how you would just keep filling this up? Now this is, we have the diagram. We're just going which one's further from the bottom. But I'll show you on the periodic table how we can see what's going on here. Then from this, we could write an electron configuration, which would just describe how many electrons are in which of the orbitals. And we list them in order of energy, so the lowest energy first. And so for manganese, we'd say, well, the 1s has 2 electrons, right? And then the 2s has 2 electrons. The 2p room has 6 people in it. The 2p, 6, and then there's 3s, 2, and then there's 3p, 6, and then the next one is the 4s with 2, and then we've got the 3d, and there's 5 people in there. If we add up the superscripts, we should get 25. 2 and 2 is 4, plus 6 is 10. That's 12, 18, 20, 25. So that's a check on, did I miss something? Any questions?
So you always just go in order.
Always go in order of energy. Yeah.
It'll always be that's what it'll look. That's the order that it'll look like, or it cannot change.
It can change, but we're going to ignore that. Yeah. There are some atoms that do it a little differently, but for the most part, we're going to ignore that. The Aufbau principle describes orbital filling. The electrons are going to occupy orbitals to minimize their energy. So we have the lower energy orbitals filling before the higher ones. Orbitals in the same level have the same energy, so then they're going to half fill before they pair up. This is the filling order. But again, we don't need to memorize that because it's hiding on the periodic table. The Pauli exclusion principle says that orbitals can hold no more than 2 electrons each. The spins have to be opposite. And then Hund's rule says that when you're filling degenerate orbitals, the electrons fill them singly first with parallel spins. So that's the electron comes in and there's a guy sleeping in the first bed and there's 2 empty beds. I'm going to take my own bed. That's Hund's rule. Okay. So here's the slide that really spells out the hotel analogy. The hotel is the quantum hotel. It's a discount resort for electrons in Mrs. K's chemistry land. So the correlations are listed over here. The floor in a hotel is the principal shell or the principal level. Both of those words get used in the text. Each room is a subshell or a sublevel. Each bed is an orbital. The people are electrons, and money is energy again. In my analogies, money is pretty much always energy. So the first floor has 1 room, it's the S room. The second floor has 2 rooms, S and P. It's a weird hotel. They don't number them, the first floor, that's not room 101, and the second floor is 201, and then 202 and 203. This is 1S and 2S, and then 2P, and then 3S, and 4S, 5S, 6S. So every floor has an S room. And once you get to the second floor and above, every floor has a P room. On the third floor, you start getting D rooms. On the fourth floor, you start getting F rooms. S rooms have 1 bed, P rooms have 3 beds, D rooms have 5 beds, F rooms have 7 beds. How many rooms do you think how many beds would a G room have? 9. We're counting by odd numbers there, right? 1, 3, 5, 7, 9. And the rule is only 2 people per bed. They have to have opposite spins. And the floor is lava, so they have to sleep together. I think this is where I meant to do what I did on the previous slide with writing in all the electrons. Yeah, pick an element. Germanium? Geranium. Do the geranium. Germanium. Yeah, whatever. 32 electrons. Okay, we'll do 32 electrons. So, they have to be red. Not sure why, but they do. So this is germanium, 32 electrons. So we just start at the bottom and start counting. So 1, 2, 3, 4, 5. This guy's going to take his own bed. 6, 7, and then they have to pair up. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. And now what's next? 4p. 1, 2. This one's cheaper. This is lower than that. Well, this is energy. In this diagram, the higher up, the more energy there is.
Like, because when you were labeling the 4s and 3d, I believe you did the 4s first.
Did I?
Yeah, that's why I understood what she was saying.
Wait, well, 4s comes before 3d.
Yeah.
Before 3D.
Uh-huh.
Okay, so it goes.
Okay, so I'm gonna number these.
Sorry.
So this is the first one, and the second one, and the third one, and the fourth one, and the fifth one, and the sixth one, and the seventh one, and the eighth one, and that would be 9, and this would be 10.
So the only reason 4S is chosen over 3D is because it's lower and goes down.
Yeah. And the reason for that is the penetration and shielding idea, that the 4s is able to squeeze through and get closer to the nucleus than the 3D is, because of its shape of its orbital, basically.
And are the rooms closest to the elevator always going to fill up before the ones that are
So on a given floor, the S room will always fill first, and then P, and then D, and then F. But you're not going to fill up that whole floor before things happen on the next floor. It gets all wonky. And just like, you go to a hotel and you're like, well, that room costs this much money, and this room right next to it costs a different amount. Why is that? Some of it seems a bit arbitrary, right? So, deal with it. That's how it is. Yeah.
So if we keep going, we would just start adding the F, right?
Yeah, if we kept going, there'd be F.
But instead of 5, there'd be 7.
Yes. Yeah. If we got to an F, there'd be 7 lines.
Will you ever give us a problem? Is that why it's not on there?
I'll never give you a problem with G. A G orbital or a G sublevel could only happen in an excited state, because we'll find when we look at the periodic table, it only goes up to the 7p. Anything above that is an excited state.
So I have a question that's unrelated to one. When it says like how many electrons are in 3p,
Mhm.
however you count how many electrons are in there, and I put like 6, right?
Mhm.
But it turns out it's like more. So I was trying to figure out what's.
So let's try to look at that specific question, because like if we're talking about the 3p sublevel, this is the 3p sublevel, the 3p room, and there are 6 electrons in there. Now if we talk about the 4p room, 4p sublevel, there's only 2 in there right now. So it's possible that there's something else going on in that problem that was confusing you. I can't tell without looking at the actual problem. Any other questions?
Will you give us a chart like this to fill out on the test?
I will not give you a chart like this, but I am going to show you that this chart is actually on the periodic table. It's in there. It's so cool. Just some notes. Really the only thing that matters are the top couple ones. Unless stated otherwise, when we say electron configuration, we refer to the ground state, everybody in their lowest energy states. Now, those electrons can move up to more expensive rooms. They can go up to higher energy orbitals if they get an inflow of energy. So maybe, I hate to think that there are slot machines in Mrs. K's chemistry land, but maybe there are. You know, they went and they played the slot machine. They won a jackpot, and they're going to blow it by staying in a more expensive room. So they can move up, but they're not going to stay up there. They're going to come down. And since that excited level is very temporary, we typically don't write an electron configuration for those. So we almost always do ground state unless it says otherwise. The number of electrons in a neutral atom is always equal to the atomic number, so we should already know that. And you could ask, well, how can you have these electrons in the same sublevel or even in the same orbital with their charges, and how does that work out? Don't they repel each other? Well, parallel spins in the different beds and then opposite spins paired up in the bed minimize that repulsion, and that's as far as I'm going with that. And then this, yeah, that's nice. So if we look at krypton has 36 electrons, and we could write out its electron configuration. And there's a whole bunch of letters and numbers, and you can see that when you get to the larger elements, this gets to be a really long string of things, right? And all of the ones at the beginning are the same. So why do we have to write them over and over and over again? Well, we don't always. So we do have a shorthand way of writing an electron configuration. It's called an inner electron configuration or a noble gas. This is the term I use, the noble gas electron configuration. So this is krypton's electron configuration. If we're writing the electron configuration for rubidium, I used up the yellow, so I'll use something else. This is the same as that. You see that? So instead of writing all of that out, we write krypton in brackets. And then we just put this 5s1 after it. So this is the electron configuration for krypton plus 5s1. So that's a lot shorter, and so it's preferable for most people, but we still need to know how to do the whole thing. You need to know how to do it both ways. You can only do it with noble gases. You can't use any other elements in the shorthand. There are some rules to this. So we've looked at hydrogen and helium, and if we continue on looking at lithium, we've got 3 electrons. This is the electron configuration. Here's the orbital diagram. So in the orbital diagram, unlike that energy filling diagram, here it's all going to be horizontal. So that fits on paper much easier instead of drawing big pictures for everything you're doing. As you're going to the right, the energy is increasing. If we have a sublevel like the 2p sublevel that has 3 orbitals, we're going to draw 3 boxes connected to each other. So I see this 1s room, there's 1 bed, there's 1 box. The 2s room, 1 bed, 1 box. The 2p room has 3 boxes because there's 3 beds. And I can look at each bed separately. So, especially at the beginning, I think it's easier to draw the orbital diagram first and then the electron configuration, even if they don't ask for the orbital diagram, just because it gets you a visual of what's going on. So, this is just showing, as I was doing in the orbital energy diagram, you know, the first electron goes in here, and the second one here, and then this one. And then here we're adding 1 more, and here we're adding 1 more. It's going up to the next room. And then here, this electron coming in says, well, I'm going to take my own bed. That's Hund's rule. And another one coming in, after carbon is nitrogen, would take its place over here. And then they would start to fill up, and then they would go on to the next room, the next sublevel. Write the orbital diagram for argon and determine the number of unpaired electrons. Okay, so argon has 18 electrons. So I'm going to think ahead. Orbital diagram, I have to draw boxes. Right? So I've got argon, and I've got 18 electrons. Right? Yeah. So if the orbitals can hold 2 electrons, I'm going to need a minimum of 9, right? 9 orbitals. So I'm just going to start drawing some boxes. So the first one is 1s, and then there's 2s, and 2p. This is all before things get kind of crazy. And then we'll go up to the 3rd floor. There's a 3s room and a 3p room. And 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 boxes. That might be enough. Actually, it is. I've done this before. Up to 3p, the order is as expected. It's not till we get higher up that things go wonky. So up to here, we're good. So 18 electrons, let's put them to bed. And go home and tell whoever cares and asks about what you did today, what'd you do in class today? Oh, we put electrons to bed. Yeah, that'll confuse them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put electrons to bed and listen to our teacher count to 18. 11, 12, 13, 14, 15, 16, 17, 18. Snug as a bug in the rug. All fit in there real nice. That's a characteristic of noble gases. They just so fill things up, and they're just really nice, and that's why they're so standoffish. They're very satisfied with themselves. So there's the orbital diagram. It says determine the number of unpaired electrons. Do you see any that are unpaired? Anybody have its own bed? No. So there's our orbital diagram, and there are 0 unpaired electrons. So sad 0. Any questions?
Are unpaired electrons the same as valence electrons?
Unpaired electrons are not the same as valence electrons. Yeah, they're not the same. Unpaired electrons are significant in whether something's attracted to a magnetic field or not, and we'll talk about that later.